Good morning, everybody. Welcome to the Digital Transformation for the Steel Industry webinar. Today we have the great pleasure to listen to Gianluca Maccani. He's Chief Executive Officer at Polytech USA, which was formerly known as BM Group. The title of his presentation today is Digitalization through Smart Robotics, Machine Vision, and Advanced Automation. Before we start the webinar today, I wanted to go through some important reminders. Unfortunately, it seems like I'm having some technical difficulties here, so I'm not able to show you the slides and get out of this this mode here. So So what I will do is I will have to unfortunately present the attendees information without the slides. I apologize for that. So I would like to notify you that the attendees audio has been disabled during the webinar. If you have any questions for the presenters, please submit them via the chat feature. The host and the moderator will determine which questions are presented to the presenter. And please note that this session is being recorded and will be available on demand replay on AIST's website. If you have any technical difficulties, please contact training@aist.org. Please note that photos and recording of the presentation is prohibited. And you will be provided a link to access presenter-approved presentations after the webinar. Due to the large size of these files, please allow 2 to 3 work days before these videos would be available online. I would hereby like to introduce to you the moderator for the webinar today, Michael Dudzik. He's General Manager, Process Automation at ArcelorMittal Dofasco. Dudzik joined ArcelorMittal in 1987 and has held various leadership roles in process automation, moving to General Manager Process Automation in 2005, and most recently to a special assignment overseeing the company's digitalization transformation. Dudzik has been involved in various advanced model and control projects throughout manufacturing and is the co-inventor of 3 ArcelorMittal Dofasco patents. I would hereby like to give the word to the moderator of this event today, Michael Dudzik.
Thank you, Alicia. Yes, so it's my great pleasure to introduce Gianluca Maccani for this presentation. Their company has done significant work in the robotics in digitalization area there. So introducing Gianluca, he's an expert and passionate about robotics, digitalization, and production processes for heavy industries such as ours. He has an incessant curiosity and desire to discover new ways to integrate robotic solution with machine vision and artificial intelligence to reduce the operator's exposure to the dangerous manual tasks in the steel industry there. Starting 20 years ago as a software developer for automation and robotics, he's now Chief Executive Officer of Polytech USA, a firm that promotes new technologies and robotics in the American steel industry. He is involved in spreading the culture of robotics in the steel industry with technical meetings, presentations, and participation in panel focused on the steel industry, such as this one there. Before I introduce him, please keep in mind any questions, please put it in the question and answer, and we'll address those at the end of the presentation. Okay, Gianluca, take it away.
Thank you very much, Mike, for your introduction. And as we said, we have some issue on the presentation. Let's see if we can work on it. Alicia is now sharing the presentation. So today I want to show you some technologies that are developed to introduce robotics, machine vision, artificial intelligence in the mills. I will follow through the process, so from the EAF to the rolling mill. In some technology, I will just jump on it and do a very short introduction of the technology. Some other that are more focused on the topics of today, I will spend some more money or some more time there. We will see an outlook on the currently available technology for the mills of tomorrow, or let's say in some case today. We can go to the next slide. So why we are thinking about introducing robotics and this kind of technology in the mill. So the first and most important thing is to reduce dangerous tasks. So there are a numerous number of tasks that are made today by operators manually, and we would like to reduce as much as possible this task and commute and change the current operator mentions from making things to supervise things. In the quality, for sure, it's very important to introduce this kind of technologies. So having a repeatable task is very important to improve the quality of your products. Automating the process, automating the controls is very important and is reflecting on the quality of the product. Help on the reduce error, for sure. And improve traceability is very important for the process. And you can improve the traceability and this kind of reduce error only if you automate the system, only if you have automatic technology that perform task. In the productivity, for sure, we have to reduce the downtime and we have also to reduce the manpower on dangerous tasks. That doesn't mean that you have to fire people, but that means that you have to remove operator from dangerous applications, reduce the manpower at the end of the day, but the turnover in the steel mill is very high. So there is no need of firing people. There is need of protecting people, having the people that work as supervisor and take a look on the process. And the youth involvement. So if you, maybe the millennials, my generation is still the generation that can work on the plant, but the new generation, the Generation Z, they are working on tablets, on multi-touch, on virtual things. So pretending that this generation is working manually around the furnace and so on is really hard. And so just promoting and involving in the new technologies is probably the best way to involve the young generation on the process. So the first application that I want to show you, and I want to just talk about that briefly, is the next slide, is about the automation crane. So this is an application that we have developed here in North America. We have some application also in Europe, but let's say here in North America is for Gerdau Petersburg. So the idea here is to keep the current bucket charging crane, but automatize the crane as much as possible. So we have installed sensors that are absolute position detection, that are sonar sensor. We have added the Wi-Fi communication to the ground to collect data from the crane. So energy and power of the drive, torque on the drives, real position of the crane, so the X, Y, and Z position of the crane. We have added the autonomous drive on the crane. So the operator from the remote pulpit, the main pulpit of the EAF with cameras can hook the bucket and confirm that is hooked, and all the other operation, the path that is followed by the crane is complete automatic. So the process begin to be measurable, repeatable, and maintenance is lowered because of this repeatable process, the repeatable path, the repeatable speed, and everything. So this is very important to start to introducing digital and autonomous systems inside of an existing mill. In the next slide, we will see something that is related to machine vision. So again, we are talking about the EAF. Right now, most of the time, the tapping is made by a pulpit that is dedicated, where the operator is physically see the tap operation. We have the installation of this machine vision system that is able to, with a thermal camera, to see the stream, is able to calculate inside of this stream the amount of steel and the amount of slag, to see the freeboard of the ladle. So from remote, the operator can see what happened, and the furnace is auto tapping the steel in the ladle. So this is another step forward in the automation in the furnace that remove tasks from the operator that are dangerous and improve the repeatability of the process. Let's start talking about some robot, and we move to the next slide. Before seeing some application, I want just myth bust some common things about robotics. So a lot of people is thinking that the robots are complicated. So I would like to assure you that the robot is a very easy machine. The anthropomorphous 6-axis or 7-axis robots are a robot that have essentially just 6 gearboxes, 6 brushless motors, and the controller that control this motor in order to follow a trajectory and a path. So in terms of construction, is very easy. In terms of software, most of the robots have a software that is very similar to .NET or Pascal. So an IT guys that coming from the schools is easily learning the software to develop a robotics application. The second point is the robot doesn't work on harsh environment. That is partially true, but there are some robot producers that produce models that are Foundry Plus, Foundry Prime solutions. There are not enough in some environment in the mill, like in front of the EAF, but the system integrator that integrate the robot can do specific protection for the robot with a layer of stainless steel, insulated and cooling system in order to protect a bit more the robot and having the application running on the furnace. We have applications that run for 12 years without major issue on the robot in front of the furnace. Robots are expensive, so the robot itself is honestly really cheap, and sometimes is most of the time honestly is cheaper than a tailor-made mechanical solution for doing the task. So it's versatile because you can change in trajectory and so on, but it's also cheap in terms of the application itself. The producer of robots are producing more than 30,000 robots a year, so based on the number, you can see that the reliability on the robot itself and the cost are lower. Robot make only repetitive tasks. I cannot integrate it in my mill because I have large tolerances. That was true since some years ago, but right now with the machine vision, with the 3D vision systems, laser beam guide or stereoscopic guide is not anymore like that. So we will see in the next slide how the 3D vision works to drive the robot in the right place, even when we have huge tolerances. The robot doesn't have human sensitivity is not true. We can work with robot having a very huge sensitivity, reducing the torque in the tool frame, so in the X, Y, and Z, and not only on one motors. So having a very huge sensitivity, defining if we are colliding with the scrap or something when we take the temperature, for example. So without bending the pole, we are detecting it, coming home, and redo the cycle without having damages on the equipment. And the maintenance costs are high. That is false because, as I said before, the robot itself, the 6-axis anthropomorphous, has only 6 gearboxes and 6 motors, electrical motor, brushless motor. So the maintenance itself on the machine is like changing the oil in the gearboxes every thousands and thousands hours of work. Normally it's like 6,000 the first time and 24,000 the next. So let's move forward on the next slide and we'll see some application of robotics. This is, for example, the EAF, sampling, temperatures, and inspection. So presently, most of the plant, when somebody have to check the refractories or the panels to see if we have some leakages and so on, is made manually by the operator, like in the picture above. So we have developed a solution together with Tenova in this case, that is able to, with a robot, with a multi-tool robot, to perform all of these operations. One, for example, is the inspection with the camera. So a big pole is inserted in the center of the furnace. The 6 cameras are looking on the furnace, and the operator is able, from remote, from the safe place of the pulpit, to check the status of the refractories, the panels, the burners, and decide if it's time to do some repair or not. Obviously, this is something that is evolving, so it's a multi-tool solution. And for example, in one of the plants in Mexico for Tenaris, they have installed a robot, like the basic one, only for taking temperature 6 or 7 years ago. And they see after that the camera coming in other plants, they have liked the idea, and they have asking us to integrate also the camera. Because of the robot, because of the fact that just adding trajectories, new path, and software is enough, they added the tool, and is a smooth transition, a smooth integration without major mechanical stuff. So let's move on the next slide. We are talking on another robot that is in the casting machine, let's say. One back, sorry. Yes. Okay, so this one is the casting robot. Again, all the system is opening the slide gate manually with the operator, fully protected, and even with all the PPE used by the operator, the rate of incidents is high in this part of the plant. So we have introduced a robotic solution with a 3D vision systems and a multi-tool again that is able to perform multiple tasks in the casting. So this task is, for example, the lensing of the slide gate in case it's not open. This is a plant in south of France. It's a stainless steel producer. In this cycle, we have changed the tool and we are removing the shroud from the ladle, for example. And in the next one, you will see the 3D scan operation for detecting the position on the nozzle and the positioning of the on the ladle shroud. So essentially, the robot automatically changes the tool, automatically detect what you have to do. This is the laser scan with the laser blade for detecting the position of the nozzle. This is a 3D vision, so we have the coordinate X, Y, and Z, and we communicate to the robot the coordinate. And the robot is moving autonomously the ladle shroud in positioning, and open the slide gate. So in the next slide, you will see what is the result of the, you can move to the next slide, Alicia, if you want. Here is the 3D scan. So the result of the 3D scan is this image in yellow. So this is a cloud point, is a mesh essentially. So what we have here is a 3D image, and the result of the 3D image elaborated is the 2 circles, the outer and inner circle that you see in that black image, where we calculate the center of the nozzle essentially. So this is what the 3D vision system is capable of, even in a harsh environment like a casting machine with a lot of dust, fumes, and so on. So moving forward to the next slide, we will start talking about machine learning applied on the on systems. So this is a project that we are developing together with Gerdau Petersburg again. In this case, they have run the first phase, that is the POC. So essentially, they have keep all the information coming from the paper filled by operator in terms of dimension of the near net shape in this case. So it's like a beam blank. And they run in a AWS software to digitalize all the information and start to learn, start to correlate this information with the 180 variables coming from the casting machine in order to try to predict the shape. In the second phase, we have installed the robot. So instead of having just 1 or 2 measured per hit, we now have the full measurement of the billet for every billet. And we retrain the machine learning model. And the third phase, we will integrate the interface for the rolling mill, for the casting machine, but also in the future LMF and furnace, in order to have the best knowledge on how to produce this steel, the prime quality billet at the lower cost possible. So in the next slide, we will see the robot working. I think that is a video you can play, Alicia. So essentially, you will see also the other robot that we have, the billet tagging in front of this, but this one is the robot for scanning the billet, the near net shape that is called. It performs multiple scans, merge all the images. We have also a thermal camera inside. So the result is the theoretical profile in blue, the real profile in white, or the thermal profile, like in this case, where we have different points where we measure the temperatures. We can also calculate the area on the left and the right flange and compare it, so we can predict what happened in the rolling mill after the operation. And in the next slide, we will see how the machine learning works, essentially. So we collect all the information, the heat and the features, and variables from the casting machine, so coolings, speed of oscillator, all this kind of information. We crunch all of this information in an unsupervised learning environment with the machine learning. The machine learning is generating the latent space clustering, and then we have the output from the system. So in the next slide, we will see what was the result with the manual data, input data from 3 years of measure made manually. So as you can see here, in the right image, all the pink cross are information that are not reliable, let's say. So that are, let's say, impossible. And that's when we start talking about installing the robot instead of using manual data as an input. And in the next slide, we will see the result after the installation of the robot. So here you can see the cluster that are more consistent. We don't have any pink cross anymore because the data are reliable. And we see a different cluster, so we can easily identify the differences between the clusters. So in this image, let's say that bottom right is the perfect billet and top left is the out of spec. So as you can see, each point is a different billet. So in the orange one, that is the BB4, so it's one section. As you can see, we have essentially 3 clusters. The 2 on the bottom are good quality. The one on top is starting to go out of spec. And because of this cluster, we are able to identify the variables that are changing this behavior on the shape of the billet with the machine learning. So the result is, in terms of shape, the fact that now instead of having one inspection every one billet per hit, we have the scan of all the billets. The operator have the immediate return, physical and visual return on the shape. You have alarm if the measure of certain tolerances. But we have also the machine learning that is working under this information and is suggesting how to change inside of the parameter of the casting machine in order to keeping a prime product producer. So the next slide is just a recap. So in terms of safety, obviously we don't need anymore an operator to go down where the cranes operates in front of a hot billet to take measure. In the productivity, because we have improved the prime quality on the casting machine, and we early detect when we are out of spec. So instead of scrapping an entire heat, we can probably fix the issue before it. And in the quality, because we have superior billet shape, so we have a better quality also when we roll this billet in the rolling mill. So let's move forward in the next slide, that is the visual tracking. I want to spend a bit more time here because it's one of the newest product that we have and prototype that we are developing together with the Whitby plant and of Gardau. So what are the current issues in a standard billet tracking solution? The first is that the tracking normally is based on sensor and signal, automation signals. Sometimes these signals fails, the sensor fails and is generating issue on the tracking. Sensors are installed in proximity of dangerous areas. So if you have one sensor that is broken, maintenance guys cannot reach this sensor and fix this sensor until you have the casting machine stopped. So sometimes generating issues on the tracking just for that reason. The current billet generation in a tracking on the casting machine is normally by the torch cut signal. So at the end of one torch cut, the billet is generated in the system, in the logical system and in the level 2. But sometimes the torch cut is not working, so the operator is cutting manually. Sometimes the torch cut signal is not good, or there is a torch cut that is not generating a billet, for example. All of these generate misalignment on the tracking and the operator have to take care manually. Normally, when there is some issue like that, the operator are busy on fixing the issue and they don't care too much on the tracking side, and that is generate misalignment on the tracking at the end of the day. Moving forward, on the run out, on the transfers, on the cooling bed, all the manual movements, if there are manual movement made by operator, that is quite common on all the trackings, also in the cooling bed of the rolling mill and so on. That is generate issue on the tracking. So when you move manually something, the tracking, the logical tracking normally is hardly follow the real position of the pieces. So the goal of the new system is to track without rely on sensor and automation signals, generate the billet based on physical image that see a billet that is long enough and big enough to be considered a billet, and to reduce the maintenance, because we will have camera. We have right now cameras installed essentially on the walls of the building that look at the billet, so are easy to maintain, are far away from the hot surfaces and the parting movement and so on. So the solution that we have identified and we have installed and we are commissioning right now is to install 12 near-infrared camera to detect and visual and see the billet essentially, without relying on sensors and without having issue during the manual movement. So we can move on the next slide. So this is essentially a view of the system. It's like a proof of concept when we use images from the standard camera of the plant to see if we are able to run the software, and that was good. So in the next slide, we will see what we have developed essentially. So here's the process flow. So from south to north is the flow of the material. So we have the 5-strand runout table with one camera looking on the runout, 3 cameras at the end of the runout. Then we have a transfer car, a twin roller way that moves 2 billets at the time, and then we have 2 cooling beds, one the south and the north. In the next slide, I will explain you the cameras. So the camera 1 is for early identifying the billets and generate the batch ID. The camera 2, 3, and 4 on the right are working to identifying the real position of the billet on the runout table and the position of the billets. Then the transfer car transfer the billet to the twin rollway, and we have the camera 5 that track the 2 billets on the rollway. We have also the list of billets on the rejection table that is west of the twin rollerway. And in the next slide, we will see the right part of the plant. So the camera 6 is the billet tracking on the twin roller on the other side of the twin roller, and where we will have the robotics tagging solution also installed. And then we have the 2 cooling beds that are able to track the billets on south and north. As you can see here, we have different color for each different batch of production. We have also different color when we have a transition billet, like the billet that have mixed steel, and so on and so forth. We have different information, like the first billet of the heat, the last billet of the heat, the transition billet, and color code for identifying, visually identifying for the crane operator the separation between the heat. So we can move for one step again, and we will have the video running. So this is essentially the machine vision at work. From left to right, we will see how the machine vision works. So if you click one time, Alicia, okay, each camera is generate an image and a path recognition on the left side. Then click again. In the second column, essentially the shape of different cameras are merged into a single image. Click again. Here we have the persistent object. So essentially, we generate the persistent object, and then we have in the fourth column, sorry, click again, Alicia, one time. The algorithm classify the object, and click again. The final result is the tracked object that we will see in this image. So you can click again, so this one disappears. So here we will see the DWG of the plant. So we can import the DWG of the plant and calibrate the camera based on that. And as you can see, we are seeing the billet in the physical real position. We have the X and Y position of the billet measured by the camera. So it's not something logical, it's not something based on assumption, but it's something based on a physical image that is moving inside of the sensor of the camera. So it's a physical detection of the position of the billet. So we have the number of the heat, the number of the strand, the number of the cut, and the physical position in the plant. In this case, the billet disappeared because the transfer car are moving the billet on the twin rollerway, and now is appearing on the twin roller. So the camera 5 that is top left is detecting the billet. The blue one will be the next moved. So we will see the billet disappearing when the transfer car is bringing the billet and reappear on the twin rollerway again. So the plus of this application is that it's like having an encoder that is measuring the position of the billet in all the places on the run out. Is not only sensors, and it's very important because we don't rely anymore on sensor. It's just the image, and there's a physical billet that is seen in the videos. Here you can see the cameras, what the camera see. Because it's a near infrared technology cameras, because the shutter is very close, as you can see the background, so the images from the rolls and so on are not in the image, is all black, is all masked, let's say, and we see only source of infrared light, that is the billet, that is hot. So it's really easy for the machine vision to identify this piece, check if it's long enough, is it big enough, and generate the billet in the level 2, and physical track the billet in the space without relying on sensor again, without relying on what happened on the machines itself. So I think that this technology is something new that is coming, and is very important. Most of the plant still have issue on the tracking, on the cooling bed, on the run out, and so on. So having this kind of technology combined with the billet tagging robot that apply on a flat tag surface the ID is the best way to having a 100% reliable solution for the tracking. I think that we can move forward on the billet tagging solution. So this is the billet tagging. Essentially, we have more than 26 or 27. It is one of the most common and standard robotic cell for us right now. That can work with a 2D image or 3D image. So again, machine vision is very important in the robotics, especially in the steel industry. We cannot rely on having the billet always exactly in the same place. So we need to have a machine vision, robust machine vision that identifies the position of the billet and check and communicate to the robot where to weld. We can move one step forward and see the video. Okay, so essentially the robot in this case is very, very easy. The movement itself are this one for picking the stud from the singularization. We have this carousel of pre-cutted tags, so you can reload it online without stopping the machine. That is very important. We have the laser marking that is burning the ceramic coating of the tag, so we don't need to have thermal transfer, ribbons, and so on. And we have a partnership with Panier about this tag, the production of this tag. This is the 3D vision that is able to identify the billets and also check the rhomboidity if needed, and take the final picture of the billet with the timestamp that is important to having the tracking on the billet. So this is our different layout and different applications. As you can see, most of the time, this application is inside of a container, a Connex. So this is because we like to having as much as possible the solution pre-tested in our factory, in our facility. Is air conditioned, all the panels, the tag station preparation, everything is inside of the container, is already done. And the commissioning is, the result of the commissioning is like 2 or 3 days, and then just following a bit the production. So plugging the power, plugging the air, plugging the network, checking the communication with the level 1 or the level 2 for the data. This is what is needed for having the robot working. So different layout, again, different solution, can be on the cooling bed, on single billets, or on the transfer car, like in this case. This is a CMC in New Jersey. So in this case, we prepare the tag in advance, and when we have the transfer car lifting the billet, we identifying the position of each one and tagging the billet on the transfer car before moving on the cooling bed the billets. So it's depending on the layout, it's depending on the time that we have available. The solution is always customized and tailor-made, but the preparation, the tag station preparation, the robot itself, and the electrical part and the software part is more or less the same, everything, every time. We have also on the welding standpoint, we have an analysis of the energy applied during the welding. If the energy is enough to mold the steel and the stud, is good. If it's not enough, because of some scale and so on that generate the problem with the arc, we physically test with the magnets the force applied on the tag. We try to detach the tag. If it's detached, we re-weld the tag. So all of this is to try to have as much as possible a reliable tagging. This is, for example, Petersburg in Virginia. Again, in front of this robot is the shape robot, and this one is the one for tagging the billet at the end of the process. So all the billet that are going to the yard on the cooling bed, let's say, are tagged, and the billet that are hot charged that are not tagged. This is another layout, seamless pipe in this case in Romania. In this case, I want to show you this video just because here we have used a different type of studs because the type of production that they do, so they essentially pierce the pipe from the billet. They don't want to have residual of studs on the billet and so on. So we use an alloy that is melted inside of the rating furnace, and the tag is loosened inside of the rating furnace, so we don't have any issue on the tag, on the rolling mill, on the piercing mill. And this is the last application that we have installed. So in this case, we don't have any space in the cooling bed and so on. It's a high productivity plant with 6 strands run out. So we just stop the billet at the before the end of the runout on the tail, and we have a bridge on top of the runout, and the robot from the top is going down and tag the billet on the tail. So different application, different solution based on the customer needs, essentially. And this is in Italy, is Beltrame, the producer. So I think that we can move forward on the next video. That is the next application that is in the rolling mill. So essentially, again, we have machine vision here, and I want to show you this application for this reason. So here we have a 3D scan, like as you see in the picture here, we have the blue blade and the camera that reconstruct the 3D surface, and the result of the 3D reconstruction is on the top left images, where you have, like in this case, unequal angles. In this picture, we can check the presence of each unequal angle, count the pieces, and identifying with the blue spot a good welding point where we can apply the tag. So if you can move one step forward, we will see the video of this robotics application too. So this is like an hammer cord of this solution from the first installation. That we can see here have probably more than 10 years. Was installed more than 10 years ago. Different brand of robot, but the technology is more or less the same. So 3D scanner, scan the bundle, identifying one good point for welding, and weld the tag on the bundle itself. There are a lot of installation of this application too. This is very important for the traceability and of the mill. So instead of having someone that manually tag the bundles, we keep any kind of issue related to applying the wrong tag or printing the wrong tag and so on. Every bundle generator is generating a signal to the robot. Robot is applying one tag at a time and is checking with the tracking if it's the right tag. So this is another application. This is in Germany. Like in this case, I want to show this because it's a complete different layout. In this case, the robot is on top of the container because of the restriction in the layout that we have. And the tag station is inside of the container. So electrical part, tag station preparation inside of the container. Robot is on top and can tag on two different places. One is the railway that transport the bundles to the yard, to the warehouse. And one is on this chain that are the bundle coming from a different strand of the rolling mill. So essentially there are two stackers on the mill, one left and one right, and one is coming from the right in this case, and one on this rollway on the left. One of the last applications that we have realized, I think that we have a couple of different layouts and systems. So in the evolution of this machine, where we have seen the wire welded on the bundle, is using a stud instead of a wire. That is to simplify the tag station preparation and this simplifying the system is also improving the reliability. Is this one? This is in Italy, for example. Is Feralpi. We have two thermal printers generating the plastic tag, one in backup to the other. We have the stud that is like for the billet tagging is a stud essentially. The robot is picking the stud, is picking the tag, is waiting for the next three bundle to come, and when they're always ready, the robot is scanning with the 3D scanner the bundles, identifying the good welding point, and is welding the tag. The last evolution of this application is using metal tag too. So one of the last installations of this robot is on the new micromill for Nucor in Sedalia, where we have the robot installed using metal tag. So the technology for creating the tag is essentially the same of the one for the billet tagging, but applied on the rebar. We have also application for tagging, obviously, merchant, so different kind of shapes. and structural, like medium section mill. So we have installation in Gerdau Midlothian, we have installation in Gerdau Cambridge, and other plants. So at the end of this one, I think that we will see this one is the one with the counting. So in this case, we have two tags, one is yellow and one is blue. The blue is when the bundle need to go in hold for the restack for some reason. The yellow one is when it's a prime product. Here we have the bundle that is coming from the rollway. The robot is scanning the face, is counting the pieces, identifying a good welding point, and weld the tag on the bundle. So here is the 3D vision. Here is the result of the 3D vision with the count and the welding point calculation. Here is the robot that applied the tag. And at the end of the welding, we are taking a picture and check if the tag is readable or not. So sometimes the thermal printer, just the transfer head, the heat transfer head is not working properly, or the ribbon is not working properly. So sometimes there are issues on the printer itself. So we are taking the picture and check if it's really readable or not, the code, and again save the times with the timestamp when we have produced this bundle, where it is now, and the tag that we have applied. So different technologies, different application, but the result is more or less the same. Here is the image of the tag with the reader of the number of the batch. And this is the last one, is the video from Nucor. So this is the application in Sedalia, is a rebar mill, micro mill. So we have the bundle coming on the rollway, the robot is going out. In this case, we have used a different type of 3D scan, that is a stereoscopic scanner. So we do the analysis of the face, identifying one welding point, applying the tag, taking a picture again, and going on. So I think that I have more or less finished my presentation. The next slide is probably the thank you one, if I remember right. Yes, so thank you very much for your attention. This is my email if you want to contact me for some question about that. And I return to Mike for the question from the attendees.
Okay, thank you very much, Gianluca. Very advanced technologies used there, combining robotics with machine learning, AI, really exciting there for the future for the steel industry. We have time for just a couple questions. We have a few from the attendees. So the first one from Brian Cook was, what sort of bandwidth do these automation solutions require? What technology do you use to communicate when the automation moves?
So I suppose that is referring to the visual tracking. And so we have, in this case, we have 1 frame per second or a couple of frames per second on the images from the cameras. The images are not compressed because we need to use it on the machine vision. And we have essentially the fiber optics connection with a dedicated network only for the cameras. So we have more or less 1 gigabyte for the 12 cameras of the bandwidth.
Okay. Next question from Koskin is, did you have any real problems with any robot you commissioned, and how was the consequence of it, such as breakdown or wrong data collection, etc.? So I guess it's the whole challenge around, commissioning, how you deal with data, breakdowns, that whole implementation phase there.
Okay. So obviously the first robot that we realized, we spent probably a couple of months before having a reliable solution that works. And obviously at the end of the day, they are machines. So you need to take care of the robot. Maintenance guys need to be trained on the maintenance of the robot itself, obviously. But in general, the robots are really reliable. We have from 12, 13 years ago. We maintain with the standard maintenance procedure once a year without major disruption. Obviously, again, there are machines that can fail, and we have the remote assistant in more or less all of our applications, so we can connect from remote. We have cameras installed in the container solution, so from remote, our technicians are able to connect to the plant, see what happened, and connect to the PLC, connect to the robot, connect to the vision system, and troubleshoot together with the maintenance guys the issues on the plant. Obviously, again, nothing is perfect, but the machine itself are reliable, so there are no major issues, I think.
Okay, one last question here from Fred. What is the level of integration of the system with the control systems of the plant? Is it necessary to integrate with level 1, level 2? Obviously a good integration type question.
Yeah, obviously we always need to interact with the plant, and probably one of the success of our company is the fact that we're born in the automation and revamping in the automation standpoint, let's say. So we still have the major revenues coming from the automation and the revamping, retrofitting standpoint. So we have more than 45 software guys just working on that. And then we have integrate from our skills and expertise in the steel industry, in the automation, the robotics. This is sometimes, especially here, we have had some issue in the first installations, communicating with the level 2, with the tracking that is present on the plant and so on in the first phases. Now we have improved a lot the solution. The software that is used by most of the plant here is using, and they have defined together with the company that integrates software how to communicate with the database, how to exchange data and so on. But obviously, again, we have to talk with the automation, the level 1 and level 2, and integrate the solution inside. And also vice versa. So the level 1 and level 2 of the plant need to know the robotic solution, if it's using Goomba software way, how it works, if it's running or not. So yeah, absolutely, we have to integrate it and discuss it during the engineering phase.
Okay, that's all the time we have. So Gianluca, thank you very much on behalf of myself and AIST for your excellent presentation. For those that have additional questions, please contact Gianluca directly. Thank you very much.
Okay, thank you to everybody.